Hi, so this is um, the shaft for the espresso grinder. These are a few of the images that I'll be submitting in on Canvas. So this is the original CAD design, and actually this is in Prepo Max. You see some forces going into the shaft, and then forces that are pulling out to show that to, to show that it's the radial force. Um, I had some technical difficulties when I was doing this, where I wouldn't get accurate lengths for the actual parts that I was creating. So when I would make them in CAD and then import them into Prepomax, they would have some really off the mark length or width or diameter. So I had to readjust some of my calculations to fit those numbers because I wasn't sure how to exactly change the length to fit the original CAD design, and rather having it as what it would be when it was imported into Prepomax. So to start off with, um, the materials. Uh, so coffee beans are abrasive and they have oils and moisture that rush sheet metal. So I went with the hybrid strategy where I used AC440C stainless steel, and it can be hardened until it's practically scratch proof, so it stays sharp for months. And but for the long shaft, we don't want a brittle hardness, and we need it to be typically tough so that it does not snap. So I chose AC4140 chromoly steel, and this is to keep it from rusting in a damp environment like a cafe. Um, so regarding the geometry, the grinders use typical grinders use flimsy pins that bend under pressure. So we used a 50 millimeter shaft that steps up to 17 millimeters at the bearing. And when you grind, the beans push straight down with about 250 newtons of force and sideways with about 100 newtons, which is what you saw here with the 250 newtons pushing down along the shaft and the 100 meters pushing down, or uh, sideways. So, and the stress we found is around 22 megapascals. Um, and our steel can handle over 600 megapascals before bending. And this shaft has a safety factor of over 10. So during the FEA analysis, this is what I have for some of the images. I changed the scale because a big factor was that it would the on the von Mises scale, the max value on the scale was very high. So what I did was I changed the max value of the scale to fit a more normal number, like 7,500, and to see what exactly was getting it, where exactly the stress was getting maxed out at on the design. So another issue I had with the actual burr interface was that we had a stress singularity. Um, so I had different CAD parts that overlap in the software, which um, was a pretty big problem. So as you can see, the length here is really large, and it's 180 millimeters. Um, so and we have a really large von Mises stress at the max point, which is obviously a stress singularity, because it doesn't really make a lot of sense for why it would be over 100,000 megapascals. So if you use the numbers that we have in the hand calculations that I did, uh, you would see that if you smooth out the boundaries and the rest of the shaft, it perfectly matches our hand calculations and rests at around 22 megapascals. So this is, if you look at the inside as well of the shaft here, I kind of, when I was designing this, I kind of separated it so you'd actually be able to see the actual shaft, and I kind of combined the shaft along with the burr itself. Um, Let me show you here as well. So if you see here, I have the burr here. You can see of a max point of around 1.173 times 10 to the power of 5 at a random point here, on this point here, along the shaft. And it's pretty obvious that the shaft here is the weakest point, probably most likely because I have it separated out to show the shaft itself and separate it from the burr. Uh, but we do have some values here. As you can see, there's resting numbers of 5,556 and relatively lower numbers on the scale, and some of these are just pretty high, which are singularities. So that is those are the main problems I had, but overall everything checks out if you calculate it with the change in the like the scale of the actual design. So overall this worked well with the materials I picked out.